Hello. You found your way back to the module Tree Phenology Analysis with R at the University of Bonn. We're still not talking about tree phenology, or R. We're still talking about climate change today. In the last lecture, we already heard about the drivers of climate change, and today we look at some of the evidence of recent warming that we've already seen. My name is Eike Lüdeling, and I'm going to take you through today's lecture. So the learning goals for this course today are that I want you to clearly understand that global temperatures are clearly increasing faster than they have ever done before in human experience. And we have to face the situation that there's really no doubt anymore that this warming is almost entirely caused by anthropogenic emissions of greenhouse gases. What you see here is an illustration of temperature change that has already occurred, that we have actually measured with thermometers and other instruments. So what is shown here is the global temperature development between 1850 and 2017. And the blue bars here, especially the dark blue bars, indicate relatively cold years, whereas the red bars, especially the dark red, are the warmest years that have occurred. And, well, the sequence that's shown here is just, well, the course of time, with early years being on the left side and late years being on the right side. And you can see that all the red bars are basically concentrated all the way on the right of this figure, which means that the last few decades have been remarkably warmer than anything we have seen before on a global average. We're really witnessing a frightening temperature increase. Here's a different type of illustration of the global temperature anomaly that maybe is a bit closer to what we're used to. And we're seeing this pretty dramatic increase here, starting probably roughly in the 1960s rather, possibly even a bit earlier, and sort of accelerating, especially if you look at the last 10-year period around here. It seems like temperatures are rising faster and faster. So this is quite concerning and, well, looks like it could cause serious problems. We can also look at this as a table. These are the 10 globally warmest years here in this list. And you see that the top 6 here all occurred since 2014. So basically, what we're seeing here is 2014, 15, 16, 17, 18, 19, all, well, the recent years that have already ended. I mean, 2020 is still going on as I'm recording this. They've all been up here, the top 6 warmest years. And below that we have 2010, 2013, also not that long ago. And all of the 10 warmest years have happened in this century, which is not all that old. In Germany, the situation is actually quite similar. Not quite as extreme, because locally there's always more variation, but we have records here since 1881. And, well, the longest ago year that we have in this list is 1994, ranked 7th here. But also here, the warmest among the 4 warmest years that we've experienced are the 2 last years. Then we have 2014, 2015. Also among the top 4. And also, except that one year, 1994, all the other years here occurred in this century, so since 2000. So also here we see a striking, well, accumulation of really warm years in the last 2 decades. So global warming is really clearly visible, and the evidence is really unambiguous. Nobody can really claim anymore that temperatures aren't going up, because that evidence is really overwhelming. And it's not only that these annual averages go up. If you start averaging temperatures a bit on a decadal scale, yeah, so we take 10-year averages, which is shown in the lower graph here, you see that there has really been this pretty dramatic kind of step pattern here towards the present, yeah, over the last 4 decades. Basically, every decade has been about, well, 0.1 to 0.2 degrees warmer than the decade before. This is a pace of change that you see nowhere else in this record, in the recorded temperature records that we have. And this is the global distribution of temperature change. All cells here that are shown in red or in purple or in orange are locations where we've seen warming. So since 1901, which is shown here, this is 1901 to 2012, almost the entire Earth has been warming, and most of this increase has been significant, which is indicated by the plus signs that you basically see all over this map. There's only really one meaningful exception to this warming trend, and that's the North Atlantic region. But this is also not particularly good news, as we'll learn about a bit later, because that could have major implications to kind of the ocean circulations. But I'll tell you more about that a bit later. We have countless data sets to support this. This is not a free claim or anything that can be easily refuted. There's lots and lots of evidence that supports this global pattern of increasing temperatures. We've also witnessed extreme temperature situations, which of course we shouldn't overinterpret. Extreme situations could just be freak outliers that could just not represent what is really happening kind of in the long term. But it is a little bit tempting to still find remarkable what's happened recently, because some recent temperature phenomena are rather scary. And what I'm talking about in this particular case is the warming that has occurred in Siberia, and basically much of the Arctic region of the planet in 2020. What you see here is the anomaly in March to June temperatures, so spring temperatures in this region, compared to the not so long-term average, the average between 2003 and 2018. This is already relative to a warm period. Yeah? So this is not comparing something to early 20th century or something. This is already comparing to the recent past. And still we see that in many parts of Siberia, the mean temperatures between March and June were up to 8 degrees warmer than what has been observed in recent decades. This is absolutely remarkable and frightening. And as you all know, this was accompanied by large-scale wildfires in this region that usually never sees temperatures above 30 degrees or something like that. And there have been records in terms of temperature set throughout this region this year. And there's a risk of positive feedback here. Again, positive feedback is not something that is good. Positive feedback is a feedback mechanism that accelerates a process that is going on. Warming in this region in Siberia, fires in Siberia, could lead to melting permafrost. And permafrost stores lots and lots of CO2 and methane in particular, so greenhouse gases that are very powerful and potent. And if these are released on a large scale, then climate change might actually get accelerated quite a bit, above the pace that we're already seeing now. Similarly, remember the lesson on the drivers of climate change, the albedo might change, because much of this region is, of course, covered by snow and ice much of the year. If temperatures go up, there's a strong risk that the area covered by ice and snow, and thus reflecting lots of the radiation that comes in, that this area will decrease and expose surfaces that absorb more heat than ice and snow would, and also this might accelerate the pace of climate change. So what we've been seeing, and what you've probably heard about a bit already, is a so-called hockey stick, and that was that term was first coined, I believe, by Professor Michael Mann, one of my personal climate science heroes, who was the first author on this paper, which came out in 1999, that described the temperature anomaly since, in this case, the year 1000. And what you see is there was always a little bit up and down, but within somewhat reasonable limits. And then all of a sudden, well, in the 20th century and still going on, we're seeing this sudden increase, very strong increase in global temperatures. This was 1998, but this is, well, now more than 20 years ago. We're now actually quite a bit higher than these temperatures are. Let's look at another hockey stick here. This has been a concept that has been taken forward by many other scientists later on, and here we have a more updated study, updated record, showing now temperatures since about well, the year 0 up to the present. And once again we see this pattern of the hockey stick, so something that goes up here very steeply towards the end of this curve. Now we see here some annotations in this diagram, because we understand quite a bit about what has shaped temperature developments in the past. Largely what is visible in this record is eruptions of volcanoes, which usually had a cooling effect on the global climate. Here's another one. You see the cooling effect. Another eruption here, not quite so clearly visible. Another one there. A couple more here. One here and one here. You also see the so-called Maunder minimum. Yeah, this is associated with a minimum of sunspots, so possibly solar radiation here was relatively low. And what you also see is like two periods that sometimes get a bit of press coverage now, because they have, of course, been cold and warm periods in the past, and sometimes people compare the current warming with the medieval warm period here around the year 1100. It doesn't actually look particularly warm if you look here. And the main reason for this is that this was a pretty warm period in Europe, but not actually on a global scale. Other parts of the world were actually relatively cool at the time, so the average temperature that we're showing here isn't particularly remarkable. Sort of the same for the Little Ice Age, even though that was, well, probably about the coolest period of the record that we know about so far. In any case, where it becomes really dramatic, I mean, even all these volcanoes couldn't really move this record very far from the normal average. But at some point, well, we invented the steam engine and started industrializing. And this really started this greenhouse effect. It was discovered around here, already in the 19th century it was discovered that it's possible, but that is actually happening, and happening fast. That is a relatively recent discovery, but we are actually seeing that this has a massive effect on temperatures currently. Here we have another barcode, kind of the same idea as before, but now we have 2,000 years here, and once again you see this kind of crazy accumulation of dark red colors here towards the end. This is not normal. We're actually coming out of a relatively cool period if you look at all of this, but now what humans have done to our atmosphere is causing a warming that is just pretty scary. It is scary because we're entering new climatic territory here. This is a very long-term diagram now of what we think the temperature, the global surface temperature of our planet was like in the past. And we certainly see pretty warm temperatures back here. Yeah? So this is more than 60 million years ago. Basically, this is just after the dinosaurs died out. Yeah? Temperatures on the globe on average was something like 25 degrees, and then they even increased a bit further towards the Eocene here. But this is a long time ago. At some point, we started a cooling trend here, and this probably was related to decreasing CO2 concentrations. We also had things happen to the ocean currents, which I mentioned in the first lecture as another driver of climate change. At some point, the Himalayas got raised up, and the Tibetan Plateau, which is a very important area for the climate today, for the Southeast Asian monsoon, for example, or South Asian monsoon. At some point, we had the circumpolar current established around Antarctica. You see here, this is when the ice sheet in Antarctica started forming around 40 million years ago. But overall, there's been this long-term cooling trend of the climate, basically starting about 50 million years ago and continuing until today, really. And then in recent years, we've had ice sheets forming in the northern hemisphere. That is still a relatively recent development. Probably started around, 8 million years ago, and possibly related to the closing of the Isthmus of Panama, which is basically the collision of South and North America and the closing of the ocean currents there, which led to large parts of kind of the Arctic region being cut off from global heat imports. Other regions, and like Europe, for example, actually got favored by this development, possibly. But it had some changes. In any case, the ice ages started forming, the ice sheets started forming, and at some point the ice ages started happening. So this is all here. You see pretty large temperature variation, and this hides a lot of the ice ages and warm ages that we didn't experience, but our region experienced in the last few million years. Currently, we're actually somewhat in the upper part of this spectrum here. We're in a warm age, whereas really the average temperature of our times, if you look at the million-year scale, is even a few degrees lower than what we'd be seeing now. So currently we have an average temperature on the planet of about 14.5 degrees. And humans have existed over about this span. Those hominins were some human-like creatures, possibly about 2 million years, but really what the kind of humans that we are probably only go back, 200,000 years or something of the sort. Now here's what we're doing now. We're raising temperatures by emitting more and more CO2 into the atmosphere. And this change that we're causing here is on a scale that is really remarkable, and especially happens at a speed that is very remarkable if you look at this long-term trend here. It's basically, on this time scale, basically this arrow is vertical. It's going straight up. And possibly we're going to confine the warming to something like 1.5 degrees or so, but what if it's more than that? It is actually hard to tell what happens if it's more than that, because we haven't seen anything of the sort. So the warmest temperatures that humans have seen, humanoids have seen, is probably something like what we're seeing now. And now we're raising temperatures possibly several degrees above that level. Possibly we could reach a warming of 5 degrees. That's what some of the climate scenarios actually find possible now. And let me just illustrate what 5 degrees means. 5 degrees sounds small, maybe, right? If it's 15 degrees today and 20 degrees tomorrow, yeah, it'll be a bit warmer. Maybe I don't have to wear a sweater, but it's not so dramatic. But on a global scale, a difference of 5 degrees is pretty impactful, because 5 degrees less than now takes us back to the last ice age. What you see here is what a world looks like that is 5 degrees cooler than what we have now, or looked like in the last ice age. We see glaciers covering northern Europe, northern Germany, the Alps, of course, as well. We see sea level being, probably more than 100 meters lower than it is now, because all the water was up here in the glaciers and the ice sheets. You could have walked to England if you wanted to. Would have probably not been very nice because it was really cold, but it was possible. This was all land. So Europe looked very different when temperatures were 5 degrees lower. But we're not talking about temperatures going 5 degrees lower again. We're talking about temperatures going up by possibly up to 5 degrees. So let's see what that looks like. We actually have to go quite a bit further back to see something that is similar to a scenario in terms of temperature to the kind of scenario that is possibly coming up. Specifically, we have to go back to the Miocene, which is 13 million years ago. And that's what the world looked like, or Europe looked like then. I mean, 13 million years is long ago for a bit of continental shift, but not all that much. And you see that, yeah, Europe is hard to recognize on this map. You can sort of tell where the Mediterranean is, but overall the shape is somewhat similar. But you also see major differences. We had a canal here going through the Iberian Peninsula, for example. We had large parts of here, the Balkans, being underwater. Italy didn't look like it does now. There were quite a few differences. I mean, look at Central Asia here, the Caspian Sea, probably being connected to the Black Sea and all. I mean, it's a very different situation in any case, and that's not necessarily what we want to go back to. I mean, 5 degrees is serious business. The kind of warming we're talking about is serious business. It's not a joke. It's not something we'll easily adapt to. It actually could possibly mean a reshaping of our land areas, moving of the seashore into areas that are now densely inhabited. Even 1.5 degrees is pretty bad. Not as bad as 5 degrees for sure, but this even the kind of warming that we're now considering the best case scenario, that will also require quite a bit of adaptation from humanity. So such changes have happened before, as we see in this map here. This is a scenario that happened in the past, but whenever these changes happened, they happened much, much more slowly than what we're currently doing. And that actually means we may already be living in an unstable world that is gradually shifting towards a different state. Because it's quite likely, I mean, we've already seen a lot of warming. It's quite likely that if this kind of, even these temperatures that we have now prevailed for another, well, a few hundred years, few thousand years, the sea level would already be higher than it is now, quite a bit higher. And we're currently moving towards this world. We're moving to a new state of equilibrium, but, well, actually no equilibrium, because we're constantly moving the goalpost even further. We're constantly adding more greenhouse gases to our atmosphere, and the consequences of this are really very, very difficult to predict. We must try to avoid this, because we don't know what's going to happen, but I can guarantee you, and most climate scientists agree, that the challenges to humanity will be massive and possibly too large for many of us. So I want to just quickly talk about rainfall. I mean, temperatures are easy. Rainfall is quite a bit harder to predict. And the evidence is somewhat messy. I mean, what you see here is observed changes in annual precipitation over land. This is from one of the IPCC reports. And yeah, it's not this beautiful kind of one-colored map that we've seen, or not so beautiful, it's a scary one-colored map that we've seen for temperatures. But we see different trends here in different parts of the world, and we see very few of these plus signs that indicate significant trends. We see some of them, though, but they're very variable. Historic changes vary strongly. Well, we do see a bit of a increasing moisture possibly in, well, North America, Eurasia, Scandinavia, Northern Australia. Drying parts of China, parts of West Africa seem to be drying quite a bit, Southern Australia, Japan. But in most locations the changes are small. And most places actually show no clear trends at all. And it is also important to consider, we're talking about a time frame of 60 years here. This is the data, what's evaluated here is a data set from 1951 to 2010. And over this time frame, many regions have seen rather massive land use changes. That is in particular true for West Africa, which has lost probably most of its forest area by now. And that does, of course, have an influence as well. It can have a very dramatic influence. China certainly has seen seen changes, also in pollution and various other things. And so it's not actually all that clear what the climate signal is here, and which of these changes are caused by other things that humans have done to the landscape. How about Germany, though? I mean, in Germany, of course, we all have seen this year, 2020, also 2019, 2018 were pretty dry, right? Very dry spring and summer. 3 dry years in a row. That's pretty remarkable. And much of our agriculture looked like this in much of Germany. So this is not a particularly vibrant maize field, and possibly not worth a lot of money. So this farmer was likely rather unhappy about this. So we have a serious moisture deficit in much of Germany currently, much of Europe. Here's a map from a couple of weeks ago that illustrates this. I mean, basically, well, I didn't put a scale here, but all the red areas, especially the dark red, are serious moisture constraints to plant growth. Yeah, but it's not so easy, actually, to detect the long-term trend here. And in analyzing climate data, weather data, it's always kind of important to not get carried away by, well, events that recently happened, because they may not actually be representative of any sort of major trend. So what I've analyzed here for you is some data for the Cologne-Bonn, the airport weather station. It's always nice to have an airport nearby, because they usually have weather stations that they have to report data from to some international authority. So you get nice data, and this is basically what we see here. Here for Cologne-Bonn. So what is shown here is the precipitation anomaly. So basically, what percentage of the long-term median rainfall fell in any given year in a particular month. Yeah, so the 12th month of the year are listed here, and then the years on the x-axis from about 1958 or so to the present. And of course, we do see these dry years that we're currently in. Yeah, so there's a lot of red here, no doubt, and yeah, it's a bit of a cluster, and we don't really see a lot of these clusters in this record. But then again, if we look around a bit, we may actually find some that look somewhat similar. And overall, the pattern that emerges here isn't really all that clear at all. I mean, this is not like these temperature anomaly bar charts barcode graphs that I showed you earlier. This is a lot more messy, and it's very, very difficult to see any clear trends here. So, I mean, statistically, there's actually no long-term trend so far towards drier conditions here in Germany. At least not here in Cologne-Bonn, and I don't think in other parts of the countries as well. Of course, climate change is not necessarily all statistics. Yeah, so a long-term statistical trend would assume that there's some sort of regular process that's going on, a linear or somewhat monotonic process that proceeds at a predictable rate. Now, with climate change, of course, other things may also happen. There may be shifts in weather patterns. Maybe some sort of low pressure or high pressure zone becomes more persistent, or we somehow get different weather because the overall climate dynamics are changing. So I'm not a meteorologist, so I can't tell you whether that is happening or not. But so far, from my kind of purely statistical point of view, I'm not totally convinced that we're going to have dry springs every year from now on. I hope I'm not. I won't be surprised by that happening anyway, because that, of course, would be very, very unfortunate and damaging, especially to agriculture in Germany. So, some conclusions from today's lecture. Humans have never experienced warming as rapid as what we've seen in recent decades. Human greenhouse gas emissions are to blame. That is very, very clear, and there's really no doubt about it. In the next lecture, we'll still stick with climate change and now move a bit into the future. We look at future scenarios that help us understand what climate change is going to do to our planet, to our biological systems, and eventually to tree phenology. Thank you for your attention.